Okay, so we have two functions, CF and H star. The last function we need appears in the equation for integrating H star. That is what?
CD.
That is CD, right? CD is the only function that cannot be trivially computed from just the velocity profile. Because CD is equal to 1 over rho UE to the cube of an integral from 0 to delta 99, basically to the outside of the boundary layer. What was it? It's tau times partial u partial y dy, right? So, okay, so I think du dy, yeah, that's right. So not only we need du dy, which we can compute from the assumed boundary layer profile, the inner layer and outer layer, we also need a tau. So what does tau look like? What does tau look like? Do we know part of what tau looks like? Tau is somewhat related to the velocity gradient, right? So if you think of the turbulent viscosity model, right? Eddy viscosity model, tau can be modeled as a laminar tau plus a turbulent tau. And the laminar tau is basically the laminar viscosity times du dy. The turbulent tau is equal to the so-called eddy viscosity times du dy. And now one insight is that if you remember the turbulent boundary layer profile, so if you have y versus u, we have a boundary layer that looks like this. Okay, and we have a significant portion of du dy. So this CD, you can either write it that way or you can write it as that way. So you can have a 0 to UE of tau times du, right? I mean, you can integrate du dy times dy is basically du, and integrating y from 0 to outside the boundary layer is basically integrating u from 0 to UE. And if you look at this, there is significant portion of this CD that can be explained by the inner layer of the turbulent boundary layer. And we know that in the inner layer, what is tau? It's just the tau wall, right? It's basically it's basically the constant. I mean, that's why we have a log law in the inner layer. It's because the tau is constant. So you can write that as a summation of two parts. You can write that as a CD inner and CD outer. And the reason we decompose that is because CD inner is very, very easy to compute. So CD inner so CD inner is equal to 1 over UE cube integration from 0 to here. Let's define this as US, right? Where the inner and outer layer meet. US of tau wall times du. And tau wall is constant. If tau wall is constant, it can be pulled out of the integration. And this is the integration just becomes what? Integration of du, which gets me what? US. That's right. Oops. Okay, so that's CD inner. And here, what is the non-dimensionalized version of tau wall? CF, right? CF is equal to tau wall divided by half of rho UE square. So tau is equal to 2 times, not 2 times, half of CF times US divided by UE. Okay, and US divided by UE can also be estimated from the boundary layer profile, right? So if we assume a certain boundary layer profile that is basically a stacking of an inner and outer layer, the location where the inner starts to, the location where the log layer starts to differ from the entire boundary layer profile is where US is. Okay, so the CD inner is very easy to compute because this one can be computed from the boundary layer profile, and half of CF can also be computed from the same boundary layer profile. We have just done that, right? Okay, so CD inner is also computable from that. So for example, we can add it at a CDI list. Oh, not here. So for example, we can have a CDI list. All right, and so here we can have CDI equal to CF divided by 2. Did we compute CF? Yeah, we CF divided by 2 times my US over UE. So here US is what? So we can take the US, for example, as the okay, so let me do this. So let me do the selection, do the truncation of UP and YP before I add the outer layer correction. Then my US can just be computed as UP end. So after I truncate the boundary layer and before I add in the outer layer correction, the location of the log layer can be considered as my US. All right. Okay, and then my UE is then right, my UE is now this. All right, so that enables me to compute a CDI list, CDI. So that's part of the CD that lives inside. Yeah.
When you assume that the tau is constant, isn't that only really true in the viscous sublayer, not in the log layer?
It is also true in the log layer. So the way we derive the log layer is by assuming tau is a constant, right? So the idea of the splitting of the inner layer and outer layer is that the outer layer is influenced by pressure gradient, the inner layer is not. Okay, and so if you write down the thin layer Navier-Stokes equation, and in the very inner layer, you ignore the pressure gradient and everything, what you end up is the equation that the laminar stress plus the Reynolds stress is equal to a constant in the inner layer. And tau here is the laminar plus turbulent stress. So tau L plus tau turbulent. All right. So and this is tau L is equal to mu times partial U partial Y, and the tau turbulent is actually I have to minus U prime V prime bar.
Yeah, I forgot about the turbulent. I was just making fun.
Oh, okay, right. So the tau here is including everything, right? So right, okay. So the inner layer tau is constant, and you can compute CD that way. And